तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the earlier talks, we saw how to write a test bench. We just started writing for a combination circuits as such, and some of you felt that the signals involved were rather large. So I am presenting now to start with more simple design as such. We have seen earlier what a test bench is. It's basically a block. You had to code it using once again the Verilog as such, and you have a design which is required to be tested. This is the design you had done. So you need to test this. So how do you test this? You have to apply what is known as stimulus. This is nothing other than application of inputs in your design module, and finally you had to see the outputs, and we will see in a minute how we do that. And so here we have seen once the design is completed, the functionality must be tested, and therefore we apply a stimulus and finally check the results. This we have already seen earlier. Now we start with a simple example. Let us say the simplest possible example can be just an AND gate. Your design has nothing more than 2 input AND gate as such, and it has 2 inputs A and B, and its output is Y. And mind you, all these nomenclatures pertain to the design module alone, not to the test bench. In the test bench we can rename this as we like and as per our convenience, and we need to test this. How to test its functionality? If you have verified the truth table is working for all its combinations, then it stands tested. And for example, this truth table for AND gate is given here for various combinations of AB, and you can also depict the same thing in terms of a timing diagram, which is shown on the left here. And A and B and Y are exactly the same sequence, except you need to read it vertically here instead of horizontally. You see these 3 entries 000 here, and that is precisely appearing here, and next entry 010 is here, and 100 followed by 1111 here, exactly the same thing. Now you also see one more time axis here, because once you say timing diagram you need to refer to a time base as such, and let us say we start arbitrarily at one point, we refer it to as a 0 point. So time starts here, right? It always goes forward fundamentally, right, unless you take the reference somewhere midpoint. So to start with, we will simplify that, saying that this is going to start at 0, and let us say time axis is marked in nanosecond, So you see that at 20 nanosecond we make a second transition here. So actually if you see here, one is naturally pointing to the high state here. So that is why we say it is 1. So 0, 1 and 0, it is flat here at the low level here. And once again this is similar explanation holds good here. And at 40 nanoseconds we have made another change to 100 and 60 111, and this can go on and and depending upon how complex the circuitry is. As far as this is concerned, you can deem it to be a complete test if you had tested all these 4 combinations here, right. So now we will apply the very same block that we have seen earlier. The test bench now is this, and this test bench, as I mentioned, it is also a Verilog file and with naturally a .v extension. Let us say we name it as and_2in_test.v, retaining the same convention that I have been telling earlier. And since the design is actually this and2in, which is here, and what we have already seen timing diagram, truth table, etc., pertain to this AND gate as such. I have retained once again the very same labels there for IOs. And here you would notice that I have renamed renamed B input in the test bench as in, right, and similarly out also I have renamed here, and in fact you can rename A also. Any meaningful names can be given for this ports. Once I say ports, it refers to either input or output, and you can check the timing diagram as you have seen earlier. Exactly the same thing you can see in a simulator, which we will be covering in the next lecture most probably. And so that is what is mentioned here, and we have a design module to start with. This is the design module, and the code, Verilog code for that is quite simple. You have only to list first identify the module, design module, which is and_2in, and this is as usual a module, and end module defines that there is a module, design module, and you need to list all the IOs here. Say A and B are inputs, and we declare here, and notice that now in the single line it has been put. Earlier we used to put line by line. Because this is a very small design, you can as well club all the inputs and outputs, and output happens to be just 1, and note that every statement is terminated by a semicolon, right. And you have also to describe what y is. Since we are going to use just an assign statement, which you have already seen for implementing this AND, which is nothing but y equal to A and B. This is the symbol for AND, which you have already familiar with. And this is declared as a wire because it is an assign statement. In design it will be wire, and in test bench it will be a different thing. So we will have a look at the two and make a comparison, and the comments are all self-explanatory here. I do not have to go through that. So this is what we have already seen in the block here. This is the design, right. Now coming to the test bench, this is what we wanted to learn, because signals were too many in the previous lecture. For combination circuits we take just a simple thing and write only a full-fledged test bench for this particular application, and then we resume where we left for the combination circuit. And now we are going to see the test bench. As I mentioned before, this file is .v extension. This file is different from this. Although you can put both in a single file and then call stimulus as you see in general textbooks, I do not follow this, because if the our ultimate goal is to design VLSI systems, so that if you see the length of the code, it will be enormous, and if you take this approach of stimulus, you will run into difficulties, because you can't make out what you are doing, because you are indulging in so many signals as such. That is why we will straight away, even for a simple example like this, we will adopt the right approach, which is applicable for any size file as such. Any big project also can be covered in the same vein. So, here as I mentioned input A here is still retained as A, and input B in the design is renamed within the test bench as N, and similarly the out connotates this Y of the design here. So, this we have seen statement by statement and that it is conforming to the design we have already pictorially depicted there. And now we start on the test bench as such. So, this is a test bench for functional checking of the design. So, put it on comments, and all titles you can use a comment like this, and we need to include the design file. That is why we have a reverse tick here, and include is the inclusion of the file name. So, this is similar to the C structure as such, and remember the quotes here to describe that this is a design file. Along with the .v extension you have to give. If you forget .v, then it will complain, I mean the compiler will complain. This is the design file as such, and we have also a time base. We have already seen in this timing diagram here that we have marked nanoseconds, etc. So, this timing will be covered in this test bench as such. How it is done, we will have a look. So, for that we need to declare a time base, that is why this has been done, and again tick here, then say time scale without any break here, it is a single word as such, and the time base actually is mentioned here. If you want 1 microsecond, you give 1 US, right, there is no mu in the normal character that you have on the keyboard. So, you use U there, right, and for picosecond P, similarly M for millisecond, and so on, different timings are there. You can refer to a standard Verilog textbook to get a little more information on this, and how much accuracy resolution that you want for this is specified here, and this happens to be a 0.1 nanosecond, and you can easily get just by dividing whatever number you have by 1000 in order to step down to next scale. From pico to nano, it is a 1000-fold difference. So, it is very handy to divide by 1000, so that you can quickly know if you want to convert it into nanosecond. And okay, we declare the module for this test bench. We have to declare the module once again, just as you declared for the design file as such. This is the place we are doing it. Okay, this is named as combination circuits because I use the very same file, therefore it appears to be different here. So, module name and this need not be same as I mentioned earlier, right, but it is good practice to maintain the same name, otherwise you can't keep track of it. Here, because I just to clear your doubts further, I added this. So, this appears to be little extraneous. So, anyway, just kindly bear with me for that difference, and we need to declare the test module as such, and no .v extension here, it is only the module name, it is not the file name. So, we just stick on only this bare minimum without the extension, and here in that some of you did not understand why reg wire here. So, it was already explained earlier, I will explain it once again. See here, if you see the timing diagram, what we need to do here is, we apply this stimuli here, A, B are stimuli here. So, we apply here and hold it till you want to change here at 20 nanosecond. So, you have to tell the system hold the value till I say till I veto that. So, that is the meaning of register here in this test bench. Are you clear? That is what we mean. We want to hold A and in. You notice that we are declaring in here, not as B, because B pertains to the design as such, whereas this pertains to the test bench. It is exactly the same signal, but we have renamed it as in here for the sake of test bench as such. So, that is how we put reg. So, in order to hold these values till you change it later on, so we need to declare it as a reg. Reg once again is expansion is register. So, it is only to say that it memorizes, right, and where we have like this. Okay, I will come back to this once again, because unless I explain this, I can't explain this. So, I will come back to this. Right now, you have to call the module design module as such. So, that is called instantiation in Verilog coding, right. So, this is the design module we started with .v extension, but that inside we had declared the module name as this alone, right. So, when you call those any of these design modules, you call only by this module name, not with the file extension, right. I hope you are clear about the file and discriminate the file and module as such. And as mentioned earlier, we can have like this any number of very same modules called several times. So, each time you call, how do you distinguish it? Distinction is done by this U1, U2 and so on. It is similar to having different packages on a circuit board as such, which we have already seen earlier. And then another thing mentioned earlier was also this what is called connect ports by name. So, if you want to connect any IO port, say for example A, B, Y are all pertain to the actual design there, whereas A in out corresponds to the test bench here. So, this is the nomenclature we adopt here. The advantage of this one is you can put A say at the last or in between or anywhere. So, suppose you forget, it is very easy for us to remember names rather than the order in which we wrote. If it has some 20 signals or 30 signals or even more, you get drowned in which order you had mentioned earlier in the design. So, you are likely you will most probably make the mistake and changing order. If you change the order, the whole thing will be chaotic. So, we call that by name. So, that is what it says here, connect ports by name. Are you clear on this score? Because this was not clear earlier, because too many signals were involved. And in fact, you can have a look at the block diagram we started, then it will become ultra clear. See, in test bench we use A in out for the IOs, whereas we use A, B and Y in the design module as such, and that is what we have already seen here. See, in design module A, B, Y is used, and in test we need to use A in and out, right. And notice that there is no such thing as input or output declaration here, because this happens to be the topmost level and there is no further higher level than this. So, everything is contained in this level. So, then what is the need for returning any IOs? IOs imply it is going to the external world, right. Mind you, what all we are doing is we are making a chip, right. Although it resembles a C program, it is not C program, it is a hardware design language, right. So, what ultimately resides in the chip will be something like this. Even this is not correct, actual transistors take its place, right. So, this is only symbolic again here, right. For circuit designers, they are familiar with this more than transistors. So, what I was saying is this 1 nanosecond is the actual time base. So, in the timing diagram we have seen here, from here to here it is marked. So, if you say suppose you have 20 there, so this time base is in nanosecond. You will have further smaller marking also in that, if you will see in the simulator when you really simulate all this. So, there will be, but fundamental unit is in nanosecond, that is what it means. But suppose it can show even 1 nanosecond here as a finer scale. This is a major graduation. It is something like your ruler that you have a scale, similar to that what you see in simulator also is like that. So, that 1 nanosecond, although you are what you are seeing outside is 1 nanosecond, what is the actual resolution, what accuracy? So, that is what is implied there by that picosecond, which is the second here. So, it simply means it is accurate up to 0.1 nanosecond, that is what. So, the 1 nanosecond is accurate to 0.1 nanosecond, otherwise you will get a doubt whether it is 1 nanosecond or 2 nanosecond, right. So, that is the difference. So, now we start on with a new thing, what is called initial. So, in these are all basically a behavioral statement as such. So, when we say initial, it's what we mean is we want to apply those stimulus as such. Here this is the core for the test bench. Suppose in the timing diagram what we wanted is, here we wanted to apply in the first instance at 0 nanosecond A and B to be 0 0 each. So, after 20 nanoseconds 0 1. So, you just remember every 20 nanosecond here we wanted to apply. So, that is what we are going to do right now. How to write that? It is quite simple. We are in 0 nanosecond if it is not mentioned. There is no harm in putting mentioning 0 nanosecond. How to mention we will see shortly. And we wanted A to be 0 and in to be 0. Mind you, we are in the test bench. So, you use in not B, right. Are you clear? Otherwise it will report error. And you apply 0 0, that is what you want for the first combination, and it should be at time 0. Now, next thing you want to apply 0 1 at what time? 20, after 20 nanosecond. So, you mention this is the special marking for indicating that it is time, right. This is how Verilog recognizes that you are mentioning after a delay of 20 nanosecond, then only I need to apply this. Are you clear? So, after 0 nanosecond you apply this, it interprets like that. Then when it comes to this statement, it says wait for 20 nanosecond. After doing this one, immediately it will come to the statement, but it can't proceed because you are saying wait. So, that is what you mean by this. So, you wait for 20 nanosecond, then apply the fresh input, and so by doing so you are getting precisely the same waveform that you have already seen earlier. Are you clear? And so is the case for other combinations, 1 0 then 1 1. And one more thing I need to mention is, we started with 0 nanosecond, then we went on to 20 nanosecond. So, what will be the time here? It says 20, but it is not 20, it is cumulative. So, 20 plus 20 you have to take, right, and that is what you understand here. So, you can see the sequential nature here if you use this timing element as such. On the other hand, if you do not put any timing, all this will be processed simultaneously, because we are dealing with hardware. In C, what will happen? You go statement by statement, and there will be delay from one statement no matter how many gigahertz you have put, right. So, it will take finite number of cycles and go to the next only after it has processed one statement. So, it is a sequential statement, all the microprocessors, DSPs, right. In contrast to that, this FPGA and A6 are all concurrent, all of them, no matter how many thousands of statements you may have here. 1 minute, let me complete this. Thousands of statements you may put here, all of them will be processed simultaneously. This is because what all these are translated right into chips gates as such, and that is the reason it is precisely the same as you had earlier with circuit boards putting so many packages, digital IC packages. Are you clear about that? Although we write like a program, it is actually end result is actually the real hardware. So, that makes the difference between a C and this. May I know your question?
Is there a provision for me to write 20, 40, 60, etc.? Because at some point, if I want to know the change,
yes.
If I want to know the time, I have to right from start. I have to keep counting, right?
Yes.
To know what is that particular time the changes.
Yes.
Is there a provision to write it?
There is no provision in this here, but you can artificially do it. Suppose you have a you allocate some variable, say a counter. We have already seen how to put a counter. So, what prevents you from putting a counter and keeping track of the actual time element, and you can see that particular counter, and you can do that only if you run, but not while looking at the code here. There is no way looking at the code, but when you execute you can have it. But even a counter is a superfluous thing, because the time axis itself will reveal where you are. So, that is also a redundant thing only, right. So, there is no provision. And then we have almost finished the test bench. So, easy it is. Now, what we say is we have already accounted for all the combinations, we give little more extra time, we run for little longer time, so as not to miss any information. For example, it will take another 20 nanosecond, right, to complete that 1 1, right. So, it would be sufficient if you put just 20 here, and you can put any number, there is no hard and fast rule for that. Only thing is make sure in sequential circuit later on when we go, we may not be in a position to assess this correctly. So, you play safe by putting a large figure there, right. And in simulator, the moment you load and run your code, pat comes the reply. So, no matter how big this value is, right, so long as it is 10 below some 10,000 or so. Are you clear? And then you have to signal that you have finished the whole thing. So, you have to then there is a special command here using a dollar here and followed by stop. It stops all this testing, right, and finally this is only temporary stop and you can resume if you wish, and I forget the command for resuming, and suppose you want to finish the entire thing, terminate the simulation, you can give this. If you do not give this also, it does not really matter, right. And finally we started with initial, then begin, a matching end is this, right, and we also started a module, so there must be an end module. So, this completes the test bench for the most primitive design, just 2 input and gate. Are you clear about this? Then with this background we can go to the next, right. This what we have started earlier. I will go little fast because you are already familiar with most of the thing, and we have already explained that, and now it should be just a cake work for you, right. So, we have seen that include will include the design as such, here in this case combination circuits, and time scale is also same, exactly the same, and that is what we put here with a resolution of 0.1 nanosecond, which was not earlier. And then we start the module, this is the test bench. So, we give the combination circuits underscore test, a meaningful name, right, and as usual we declare all the inputs, and inputs are all marked here A, B, C. You remember that we had done so many logical gates, right, and here is the one if you want to recollect. All this we have already covered, and that is precisely what we have here, right. And here in test bench you have to declare all inputs as reg in order to hold the value, right. So, we saw 8 inputs for 8 input mux. Then we had a magnitude comparator which compared 2 numbers, and they are all inputs. What we are going to speak up to this point are all inputs as such. So, here size is also taken into account, and I had forgotten that wire earlier, right. I did not explain that wire earlier. So, I will explain it here because it is fundamentally the same, and here we may have, we have already seen we are how to invoke a design module, and you may have several design modules, and you may invoke that. So, in the course of invoking you may like to have one of the signals or more of one or more of the signals from one module to be used in some other modules. So, how do you declare those signals? You declare them as a wire, because it is a physical wire from one IC to another, its counterpart is that, it is analogous to that. So, that is the reason why we declare it as a wire, right. This is applicable only in the case of test bench, do not confuse it with the design, there the declarations are entirely different, right. So, based on the environment you are placed in, you have to see. So, the logical reason is clear here, right. So, we want to physically connect, that is why it has got to be a net, and the keyword for net here in Verilog is wire, that is why we do this, and these are all single bit outputs. And this dimension we have seen here are all listing of outputs for various combinations. We have done behavioral, full adder, then data flow, and gate level, all these are listed here, and this for the magnitude comparator outputs, all of them up to 18, and then we had one more design example wherein two numbers are summed. We have already seen n1 and n2 earlier, and corresponding outputs are this, and once again all outputs are declared as wire. Now we call this combination circuits design. We instantiate here. Like this we could have instantiated different modules. If there are more than one, we could have done, and any signal that use may have to be connected to another. That is why we had to declare that particular these signals as wire. I think it is very clear now. And connect ports by name, this also we have seen, and I will rush it through because it is precisely what you have already seen. Right, I was here. And last one should not have a comma separation, right? That is what is here, and you complete the brackets here, and once again here also you have an initial. Now we are going to apply the stimulus. This is quite a little longer because you have so many signals there, and so first at 0 time we will this is selector's input here, and we apply 0 0 0 here, right, and we also need for mux, and we just initialize all of them to 0 here, and we have a magnitude comparator. So we use just two numbers, remember 200 and 199, right. So if obviously 200 is greater than 199, so a greater output, more output will be set, and so on. So you can keep on changing your input data for various combinations. You keep on changing. At 0 time I apply all these inputs, and then and keep on changing at different points of time. At 10 nanoseconds I am changing one of the mux, I am applying just one. So I will be applying systematically one after another, so that it will be easy for you to look at the simulated result one thing at a time. Otherwise you will get bogged down in details, right. And now I change once again after 10 nanoseconds I am changing the either the same inputs or some other inputs, fresh inputs may come into being here, right. So some of them you can see here, and we will not really worry about these things right now. When we go into the simulation we will refer to this and go in more detail. It is sufficient that the whole thing runs in the same sequence, right. So at 10 nanoseconds I am just advancing it by 1, the selector, so that we can have I1 processed. Once again here I1 is still made 0, I just want to delay that because I wanted to put some more numbers for other modules. So once again after 10 this is cumulative, so now I think we are in 20 nanoseconds. So you have to unfortunately keep track, but you can always keep track by keying it as a comment here. So that is why I had put at many places, and once again all the inputs. Mind you, this is a stimulus is only for inputs. You need to only apply input as such, right. So simulator will tell you, I mean give you everything in one shot on as a waveform, right, both inputs as well as outputs. So you can see that comment here. So I have kept track, right. At 40 nanosecond again I change different inputs. In this vein it keeps going, so I do not have to go repeat the same thing, and I will finally go into the end. So 140 nanosecond, right. So it has taken so long, right. How much then we give some more cushion there, so that this being a combination circuit you do not have to really give much cushion, maybe 20-30 nanoseconds would suffice here, but still you can play safe, right. But it will be it may be required in sequential circuits, as we will see right now. So that is what I have commented here, run long enough to test all possibilities, right, and the possibilities may spill over beyond this time. That is why we need a cushioning, and as usual we have a stop. I have deliberately omitted finish there because it is not really mandatory as such, right. So, finally, we have an end because we had a begin, initial begin, is that correct? And we put everything in a module. So, corresponding end module must be there. So, this completes the test bench for the combination circuits. Just figures alone are put as far as combination circuits are concerned. This is what we have already seen just now for the test bench. And now we will see the sequential circuits test bench, right. And we started with 2 registers, and you can use it for delaying or pipelining, and then we have a counter realization and monoshot realization here, and shift register, and 2 varieties of shift registers were there, although pictorially it is only one here, right. And then we saw a parallel to serial converter as such, and a state machine model also we had seen, and finally we have seen a pattern sequence detector. So, this is what we are going to go for the test bench as such. Once again here you declare give a meaningful name as to what you are doing, and then define is a new thing that we are introducing here. So, here we are dealing with a sequential circuit. So, we need to create some clock, a free running clock. Without a clock there is no life in a sequential circuit. For that matter, any digital system needs a clock, and a clock in actual practice, when you finally make a circuit, I mean a chip, there a clock generator will be there, and that will feed into the chip as such, which you finally design. But what do we do in the simulation environment? You have to create it once again by the Verilog coding itself. So, in order to facilitate this one, we first define what is called a clock period by 2. This is the name that I have given. If you feel it is too long, you can give any other precise name. See, all this are like a C program which you can give, where you can give meaningful names, right. And what we say is this is unit of time. So, this implies there must be a time scale definition also, and it may your compiler may give a warning, but you can overrule that warning, and you do not have to put time scale every time, right. You have already taken into account in the test bench. So, you need the time scale only for the simulation. Mind you, this all the times that we have spoken, hash, etc., and all this will be filtered out in the during the synthesis process, because we said that the Verilog designing fundamentally using RTL coding guidelines is to get rid of the technology dependence, right. We should be independent of the technology, and that is possible only if there is no time element, but we have introduced time element just to facilitate simulation as such, and therefore it appears only in the test bench, right. During synthesis it will reject the test bench, and that is the reason why we give in the design we include all the down files, submodules of the design inside the design, and include the design top design file only in the test bench. Are you clear? So, this implies you can treat it as a variable here. So, this is again a behavioral thing, just like initial, right, and they are not RTL compliant, mind you. So, we have seen earlier what is RTL compliance and what is not. So, you should discriminate the two, and as usual we are what we this is equivalent to saying a variable called clock period by 2 is equal to 10, that is all it means, right, and we include the design here, and we declare this test bench module, and again a meaningful name, and we declare all the output inputs as reg and outputs as wire. That is what you see here, all this up to this, right, and all these are wires, these are all outputs here, and multi-bit precision. So, we have seen a state machine. So, those outputs are also listed here, and this out corresponds to we have a pattern sequence detector. So, that in and out single bit are this, right. So, this happens to be the output for that. So, we declare it as wire, and we had some counters, etc. I remember not for what module exactly, and you can always make it out. At the time of simulation you will see in detail, and some end of conversion is there. So, I think that was a parallel to serial conversion we had done, right. So, pertaining to that these signals are. And then we instantiate the design module. This is the design module which we call here, we call it instantiation here, and as usual you can give the chip chip name, right, instance name here call, and list all the inputs of the this mind you we are doing this for the design. So, you adopt that calling by connect ports by name we have seen, that is the nomenclature we give, right. So, here you would appreciate that need for this, because suppose I had forgotten and put instead of beats here, right, it will be chaotic as I mentioned earlier. So, in order to do that we have called by name as such. So, this lists precisely all the IOs here, and what it is mentioned here, inputs of state machine here, this in1 and in2 we used in the state machine, and trigger is the monoshot input here, and then all these are pertain to the monoshot here. It says then outputs of parallel to serial converter. We have already seen earlier corresponding inputs, and these are all the outputs here, right. And outputs of the state machine is here once again listed. Note that all of them are same. Here one thing I can mention, that was the doubt raised in the earlier lecture also. You can have different name here, because this pertains to this test bench as such, whereas this pertains to the design. In design you may call it by one name, and here you may call it by a different name, because see for example for out here you may actually be using a counter, not the out. So, what you do is of course if it is a single bit it has no meaning, a counter. If it is a multi bit, for illustration I am saying. So, you can redefine in this particular test bench you may be using another counter which you want to connect, right, here. So, what you do is you can call it as a counter 1 or something like that, right. So, only thing that should match is dimension of this variable, this signal and this signal, is that clear. And we have completed a listing of IOs here in the instantiation, and that is why we have the end here. And once again we have initial, and I do not have to go step by step in this, and what all it is sufficient to say that all the inputs that we need for testing this whole sequential circuit will appear one at a time, right. When the time is ripe for that, it will strike here. For at 0 time you initiate all this basically some of the inputs used here. Say ABC are the inputs used for setting a reset of a register and so on. So, we have now this we have not covered as such. Clock we said is what we are going to generate, and we saw that earlier having defined clock divided by 2 or something like that and equating it to 10. So, what it means is it means the clock half time, it is not the time period, but half the time period is 10 nanosecond. If you had defined 1 nanosecond, declared the time scale as time base as 1 nanosecond, that is what is implied there, right. And now you had clock is actually a variable here, it is a behavioral, purely behavioral statement, not an RTL coding confirmation, right. It violates the RTL coding, right, this clock, because it is only to create clock for the sake of simulator. It is not the actual chip level clock which needs to be generated separately using another IC or whatever. So, you initiate reset, then trigger is for mono shot, then if you want to hold all that. So, you can make it either 0, that is a low, that is inactive state most of them, and active state is 1, right. You can also use this this notation, meaning that the 1 stands for number of bits here. So, it happens to be only 1, and what it is, it is a 0 level, low, right. In binary you have only 2 states, 0 and 1. So, B for binary, this tick also you will have to put, and then here we had I think this shift register. So, we need to set data, right. So, that is 16 bits. I am setting it to AAA because this generates alternate ones and zeros. So, if you can also write it in a binary if you wish, and so that is what you have here, precisely the same thing, and this appears to be slightly different. Data out pertains to parallel to serial converter, right. So, this is the example, correct one. Then we apply different inputs for this when it should be shifted, then right or left, right. So, for state machine we need in 1, in 2 and so on, and we change the stimulus now. So, after 20 nanosecond it has been changed from 0 0 0 to 1 here, right. And similarly, now only we are applying the reset. This is the power on reset we said, or system reset. So, earlier had you noticed that one, it would have been 1, right, it is 1 here. So, to start with it was 0 nanosecond, let us not reset immediately, we will give some time lag and then reset the system, right. 1 will not reset because this negative here. So, it is active low, that is what we have already seen, asynchronous active low. So, after that we bring it back to 1 from 0, after 20 nanosecond we bring it back to 0, 1. So, that normal working of the sequential circuit can commence. Only subsequent to this positive edge clock will arrive, only from then onwards its system starts working. So, it is the whole affair goes within 20-30 nanosecond, right. At 40 nanosecond you can see 40 subsequent to this clock must arrive. So, it may arrive somewhere in between here, right, around 50 nanosecond. When we see the simulation we will see that exact timing, that you can find out because that clock variable we have given, we have made it 0, we will come to that later on, when it will change we will see. So, that determines the rising edge of the clock. It was 0, then when you make it 1, so naturally a rising edge is encountered, and similarly you keep on changing for various inputs. So, that is what you see here, right. And this is for the sequential machine, basically in 1 and in 2. Yes.
Actually, I don't have any idea.
So, this is a pattern sequence detector, and for that here you notice that all along I have been using 10, 20 and so on. I have made this deliberately 5. Had I put 20, this pattern sequence detector will not work, because for simple reason that I explained earlier also while describing this, and you have to apply positive edge of the clock only after subsequent to applying a data, and the data must be stable. By doing so, I am applying 5 nanosecond earlier the data. I am applying the data so that it will be valid when the actually clock strikes, right. So, that is why this is there, and again all the inputs change, and finally we will go to the end. So, these are all nothing but the same pattern. Every 20 nanosecond I am changing the input pattern as per the pattern that we have already listed earlier. And once again we want this being a sequential circuit, you give more cushion. Arbitrarily I gave this one. After running the simulation you will know that it may not be required. So, you can always come back, change to what you want, right, thereby quicken the simulation process, but it is hardly noticeable for these values. So, you do not really have to worry about that. And finally, the test bench is complete with a stop. and a dollar finish, right, which I have not put here. If you wish, you can put that. And finally, an end is there, and we have not ended the module, remember, so far. So, now comes your question, which will be answered in one statement, as I said. See, we said after clock period by 2, this was equated to 10 there, which implies 10 nanosecond. That means you take this decision only every 10 nanoseconds afterwards. This applies for every 10 nanosecond. So, this means I said that all the statements are concurrent as well, right. So, this is always block, separate block as such. So, here there is no begin, no end, because it has single statement here, and this clock is, notice this, it is inverted, and this symbol is used for equal to, as I said before, always block must always have this symbol, not the equal to, right. In assign and initial blocks, etc., you can use that equal to. Are you all clear with this, right? And that is how it will toggle, right. Finally, for a module, you need a matching end module as such. With this, I complete the test bench, and if you have any questions, I will be happy to answer right now, or offline you can ask.
Can you elaborate on that last module, clock module?
Which one? This clock. So, we started with clock equal to 0, right, and what is 0? If you invert, you will get 1. So, this will happen every 10 nanosecond, because this is 10. So, time at always means that always after 10 nanosecond do this. So, 0 will be 1, 1 will be 0, and for eternity it will go on till power fails, right. Next time we will see how to use the modulator, I mean simulator as such, and thank you.